this here. If you have your phone, otherwise I've got it on my iPad, so I'll just show you. But it's going to be really useful just to be able to quickly graph something to see what it looks like, to check behaviors. And so if you download, it's called Desmos, blah, 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 it'll look like this, okay? But I'll just show you. So if you don't want to do it right now, then that's fine. But if you want to follow along, maybe get a head start on the download if you don't already have it. Well, let's see here. Okay, so download Desmos. Which is a graphing app. Because the kind of concern, and Kate's going to be, so Kate from the Learning Center, she's just going to pop by today. But she was kind of concerned because I guess last term they spent a lot of time, shifting graphs and how do they move, how do they behave, and she said, well, that's not really, like that's hard, that's really hard, and do you need to know that? Not really, okay. From the math standpoint, it is important to know what what a function might look like, right? Because that tells you what kind of behavior to expect. And so, so for that reason, when I saw in the textbook that they use Desmos, I was like, oh, cha-ching, I get to learn Desmos. Turns out there's nothing to learn. It's really simple. So, wah, wah. But I've been meaning to check it out, and so this was kind of my nudge. And it is really handy to have just on your phone, right? Oh, what does this function look like, right? And so we'll play around with Desmos a little bit. Okay. Bless you. Okay, let's see here. Oh yeah. Last day I was so ambitious, overly ambitious, I guess, with our examples. So we're just gonna wrap up example 1, and then I've cut example 2. We're gonna do example 3 with the exception of part C. And then the rest have been cut. They're obviously in the textbook, but these are the ones that I kind of wanted to have a run through with you, okay? Mostly for the assignment. And so on Moodle, I said the assignment I had written, assignment 3 will be handed out in class on Thursday. It'll be due on Thursday next week. But because we've got our review that day, I've decided to make it due Tuesday, and then you can have it back for the review day. So that's really just for you to have more feedback before the test. And so I've made it due Tuesday, but I've also made it short. So yeah. Yeah, so I'll give you a practice test on Tuesday, and then what we'll do on Thursday is we'll go through it together. Just kind of highlighting things to keep track of. Okay, so not really doing any review, but continuing example number 1 from last day. Where did we finish? Let's see here. Oh, we found the range. Okay. And so we found f of t when it's equal to 83, and we decided, okay, well, that's 2 inputs actually yield an output of 83, 8, and 10. And then we listed the range, keeping in mind, right, that the range and the domain are sets, okay? And so we use set notation, and what we do is, well, I like to list them in order, right, from smallest to largest, but also we take out any duplicate values, right? And so we only list unique values in the range, right? We had 2 values of 83, but we only list it once because we only need to list it once. Okay. So from here, part 4 and part 5, what's the minimum and the maximum of f? It's pretty easy to see, but I'll just steal this here. You have it in your notes, so I'm not too worried. So we said the range of f is this, just as a reminder. And so part 4 says find m. Lowercase m is the minimum. Well, because I've listed these from smallest to largest, right, it's going to be easy to find the minimum and the maximum. The minimum is 64 and the maximum is 83. Find m. M is 64. And then part 5. Oops, that's not a capital M. The maximum is 83, right? And remember, we denote the maximum by a capital M. Okay. We're going to see more lowercase m's that don't mean the minimum, but it's just going to be a matter of context, right? Am I talking about the minimum and the maximum, right? Or am I talking about the slope of a straight line, y equals mx plus b, right? And so those are very different things. So it's kind of safe to have the same variable for both of those, okay? But just something to keep an eye out for. So part 6, I've cut because we're going to doing in section 1.2, which we'll be moving on to. So what we said last day was that this is a discrete function, right? And so we only know the temperature at 0 hours after 6 a.m., 2 hours after 6 a.m., all the way up to 12 hours, moving up by 2-hour increments. So we don't actually know the behavior between those points. And so we can guess what it might be, right? And it's going to be a reasonable guess, right? But as far as the function goes, we don't know how it behaves. And so we call this a discrete function, right? Because we've got these discrete points that make up a function. And so typically what we have are continuous functions. And so continuous functions are when we have straight lines or even curved lines, right? As long as they satisfy that vertical line test, where if we draw lines through it, as long as we only cross the line once, right, then we have a function. And so to make this continuous, what would we need to do? The problem is that we only have time points 0, 2, 4, 6, 8, 10, 12, right? And so to make it continuous, we would need to continuously measure the temperature, right, and record it. Okay? So in order to make this a continuous function, we would need to measure the temperature I guess I said measure, but I really mean record, measure or record the temperature at every time point between 0 and 12.
So that would be, there's going to have to be an interval of time points, right?
Yeah.
Because otherwise it's...
So the problem is that that's impossible to do, right? And so typically what we end up doing is we end up modeling this behavior, right, with a function, right, with a continuous function. Okay? So we know that temperature exists at every time point, but for us to be able to record it is impossible at every single time point. Cool. Any questions about that one? Cool. So we're going to do example 3. So like I said, and then we're not going to do part C. I had to really go in and slash. Can't be spending time like we did last day. Well, these concepts are important. Yes, they are. I know. I want to talk about all of them, but we can't. So we had to get down to the nitty-gritty. All right, and so here I've given you a function. So let h of t, that's fine. So h is the name of our function. T is the variable, right? The independent variable. And basically whatever variable you have in here, right? That's what your function is a function of, right? And so h of t you can replace with y if you want, and t you can replace with x if you want, right? They're just variables. Okay? So we're gonna start off easy, right? And find things like h of -1, h of 0, h of 2, and then we move into things like h of 2x, right? And so the thing that you need to keep in mind is that we're just gonna, wherever you see a t, you're gonna replace it with whatever's inside the brackets, right? And so we've got example 3. Part A. And because I have to scroll up here, I'm going to write the function h of t is -t squared plus 3t plus 4. Okay. So h of -1, being careful with these negatives, right? So we've got -1 squared plus 3 times -1 plus 4. And absolutely use your calculator. Are you crazy? Yeah. Okay. The square of -1, right, is just +1, but we still have the 1 or the negative out front. So we've got -1 plus -3 plus 4, right? Which if we simplify is -1 minus 3 plus 4. So -1 minus 3 plus 4. That's 0. No, not that many. I want to see work. And so my main complaint, let's say, from assignment 1 is you need to show all your work, right? And so even if you did it, I know we were tight for space on that one because I had to arrange it somehow. But even if you continue your work on a separate page, then just staple those together. And so, because I'm not concerned about the answer, right? I'm concerned about how you got to that answer, right? And so, and we could be a little bit neater in general, I think. I think it was a space issue, but we can work on that. Okay? Me too. I'll give you more space. How about? Oh, before I forget to mention it, I did put a note on question 3 on assignment 3 that it's continued on the next page, but I don't want you to forget about it because it's a doozy back there and it's worth 5 marks. So back page, don't forget it. Okay. She's a doozy. Okay. I guess this was I. So far so good. H of 0, so now we're just plugging in 0 for t, and so we've got negative 0 squared plus 3 times 0 plus 4, which is negative 0 plus 0 plus 4, which last time I checked is just 4. Okay. What are these two things telling us, right? If we have a value of t, or if we think about it in terms of a graph like this, t is our independent variable and h of t is our dependent variable, right, on our y-axis, then what this is saying is when t is negative 1, right, so over here, then h of t is 0, right, so we're on the x-axis. So here at negative 1, make it a little bit clearer, right? What's this telling us? When x essentially is 0, right, y is 4, and so here at 0, so t equals 0, we're at h of t is 4. Let's just pretend it's there. 0, 4, negative 1, 0. Okay. So already we kind of see a little bit of what this function looks like. Okay. So let's keep going, or let's stop. Oh, you're all here. So I'm going to pause the recording just so you don't have to feel self-conscious. Start this again. So I'm guessing you've stopped by the Learning Center to check it out, at least just to check it out. But if you haven't, Kate's really helpful, and she's like the jack of all trades of all things science. I guess it's insane how much she knows. I don't know how she does it. But okay, let's keep going. H of 2 is negative 2 squared plus 3 times 2 plus 4. Now, you want to keep those the brackets on here, right? So you want to make sure that if you've got a negative value for t, then you want to keep those brackets around those negative values so you don't lose them. And even positive values, I just keep them in brackets there. Okay. And so we've got negative t squared, negative 4 plus 6 plus 4 is 6. Anyways, I'm keeping the negative outside. I guess we'll see. Oh yeah, because it's upside down. All right, so let's kick it up a notch. How about, so we've got part 4, which says, okay, I want h of 2x. Yeah.
How do you, like, when I was just doing them ahead of you, whatever, like, I was, how do you know to keep the negative, like, outside of the brackets?
Well, that's, so, yeah. It's because it's negative, like, so it's t squared, but then it's negative, right? So you want to keep that negative. And so the reason I know that is because it's an upside down parabola. Hey, helpful to know what it's going to look like, right? And so, but yeah, so the t is squared, but there's no point of having negative t squared, right? Because that would just be t squared. And so, yeah. If I wanted negative t squared, I would have had to put brackets around there. Okay. Which I don't. Okay. All right. H of 2x, oops. Drawing with my eraser. H of 2x, so same idea. I'm going to plug in 2x wherever I see a t. And so it's going to look a little bit different. So negative 2x squared plus 3 times 2x plus 4. So I'm replacing a variable with another variable, essentially, right? So I'm still not going to be able to find the value, right? But we can simplify it. And so we have negative, and just be careful, right? Because the square actually goes on the 2 and the x, right? Because they're multiplying inside. And so 2 squared times x squared plus 6x plus 4 is negative 4x squared plus 6x plus 4. Okay. What if we wanted to do 2 times h of x? That's different, right? Because we've got 2 on the outside. And so here, we're multiplying our x by 2, right? Here, we're multiplying our h of x by 2. Those are completely different things, right? So what you're going to do is, well, the h of x just says, wherever you see a t, replace it with an x. We can do that, right? But then multiply it by 2. Okay, so we've got 2 times, and then in brackets, negative x squared plus 3x plus 4. We're going to expand and simplify this, right? And so someone called it feed the chickens the other day, because you have to multiply it in, so you're feeding all the chickens. I think that's pretty cute, but I was like, oh, I get it. So we've got negative 2x squared plus 6x plus 8. What if we did something even crazier, like h of t plus 2? Right? Just keeping your wits about you, right? Replacing, wherever you see a t, now replace it with t plus 2, but in brackets, right? Because the t plus 2 has to stay together. So you've got negative t plus 2 squared plus 3 times t plus 2 plus 4. Okay. Yikes. The t plus 2 squared, right? I always just write them out next to each other because then I can feed the chickens, I guess. And I'm going to move my equal sign over because I can tell I'm going to need more room. And so what I've got is negative, and then t plus 2 times t plus 2. Notice how I use my brackets here, right? So I'm rewriting t plus 2 squared as t plus 2 times t plus 2, but then I know I need to negate all of that, right? And so I'm keeping the negative outside, and I'm putting this chunk in another set of brackets, right? Don't be stingy with the brackets. Right? And then plus, you know what? I'm just going to expand 3 times t plus 2 right away here, save us some work. 3t plus 6 plus 4. Okay. So now the work is just going to be expanding t plus 2 squared, okay, which is the negative of t squared plus 2t plus 2t plus 2 times 2 is 4, bless you, plus 3t plus 6, oh, I guess I could just write 10. I'll do a double whammy here. I know I can collapse 2t plus 2t into 4t, right? And then I'll also bring the negative in at the same time. And so we're going to have negative t squared minus 4t minus 4, remembering to add that negative onto all of the terms in there. Don't forget about 1 or 2, plus 3t plus 10. We can collect the t's and the 4 and the 10. Constants, bless you. Negative t squared. Negative 4t plus 3t is negative t. Negative 4 plus 10, 6. Nice. Good. What if we have h of t plus 2? Sounds the same. H of t plus 2 or h of t plus 2. They're different. Right? And so we've got h of t, well, that's just negative t squared plus 3t plus 4, and then plus 2. Simplifies to negative t squared plus 3t plus 6. Too easy. That's it. Womp womp. How about h of t plus h of 2? Let's skip this line break here. H of t plus h of 2. We know h of t is just negative t squared plus 3t plus 4. And then plus, and I'm going to put it all in brackets. I think we solved for it already. But just in case, right, we did solve for h of 2, so you could just put in 6 if you want. But just to show, I'll do it again. Oh, maybe I don't have room. Hang on. I'll make room. Plus -2 squared plus 3 times 2 plus 4. Having a eureka back there. Eureka! Did you guys have to watch those in high school? Anyways, it was fun days when they brought in, like in science, they brought in the TV, and it was like this little blob. Oh, it was like huge, but like not in a cool way, like width. Yeah, the VCR. They plug it in. Gotta fast forward to the part they want. But anyways, it was this little cartoon. Eureka! Bill Nye the Science Guy. Yeah, I think we only had Bill Nye once. We only got to watch him once. Oh yeah, he's way better.
We had Hank Green the other day, so that was a big
I don't know what that is.
SciShow Space, SciShow Psych, SciShow, like the entire SciShow series. That was the crash course, the YouTube crash courses for like any of the subjects, science, biology, history.
I know Sal Khan.
Wow, okay, yeah. It is more less scholastic, more information. Yeah, it is like
Cool. Oh. I know. I'm about to do the same. How about that? -t squared plus 3t plus 10. Which is what you'd expect, right? Because we already knew that this was supposed to be 6, right? And so if we just add 6 to h of t, then there we are. Okay. All right. We want, so part B. Oh, any questions about those? Before we got sidetracked about educational videos, I guess. We want to solve h of t equals 0. Okay. And so, let's see. Here, don't think so. Okay. We've got negative, or sorry, I'll rewrite the function because I keep scrolling past it. H of t, remember, is -t squared plus 3t plus, is it 4 or 2? 6. 4. So we want to solve and force this to be 0. What does that mean? It means we're solving for all the points where this line crosses the x-axis, right? We already found one of those points, right? Just by happenstance. Well, probably not, because, I mean, there's some thought that goes into these books, but, right? At x equal, or t equals -1, we found that h of t is 0. So that's one of those points. We have to find the other one. And so here, we've got a quadratic equation. I like the quadratic formula instead of factoring, because I find factoring, I don't know, it's like they have to multiply to this and add to this, and I don't, sometimes it just doesn't click to me. So I like to just use the quadratic formula to find these zeros. And so if we force this to be 0, -2 t squared plus 3t plus 4, we call this finding the zeros. Finding the zeros. Zeros. Okay. Since this is in the form f of x is ax squared plus bx plus c, we can use x is negative b plus minus the square root of b squared minus 4ac, I'm just going by memory here, over 2a. If that's not, but I feel like got it pretty good in the old noggin. So in our case, right, a is -1, b is +3, and c is 4. So we've got -3 plus minus the square root of 3 squared minus 4 times -1 times 4 over 2 times -1. So we've got -3 plus minus the square root of 9 minus 4 times -1, so that's going to be plus, right? 4 times 1 times 4 is 16 over -2. Okay. One thing you want to keep in mind, right? We talked about in terms of the domain, right, or legal math, we cannot take the square root of a negative number. Right, and so if you're doing this and you're finding that this subtracted from this yields a negative number, you've probably put in the wrong values here, right? And so you want to make sure that you're always taking the square root of a positive number, 0 or positive. And so 9 plus 16 is 25, and so we've got -3 plus minus the square root of 25 over -2. And this is all over -2. So what we have is -3 plus minus 5 over -2. So x, or I guess in our case, t, so t is going to be -3, let's do plus 5 over -2, which is 2 over -2, which is -1. And t is -3 minus 5 over -2, which is -8 over -2, which is 4. We knew the first one, right? We knew it crossed the x-axis at -1, right? But now we also know that it crosses the x-axis at +4. Cool. What did I ask you to do next? And you can plug these in, right? You can use t equals -1 and find that the solution is 0 like we did. Or if you want to check it, you can plug in 4 for t and check that it equals 0, but it will. And so part C, we're skipping, sad face. Part D. All right. So here's where we're going to use Desmos. So I'll just show you on here, I guess. It's going to look a little bit different on your phone because it has to be stacked, but I think in general we're doing okay. Okay. It's got some prefab stuff going on here, and so we'll use x for the x-axis and y for the y-axis. And so we've got, so wherever we see a t, in our case, we're just going to use x. Doesn't really matter. And so we've got a negative. I thought there was a negative, but no. I guess we just do the minus. Not really the same, but minus, and then x squared. So notice how there's a squared button here. So if you plug in x and then squared, right, as you go, it'll go through and, oops, right, it'll just draw whatever's in the space at that time, right? So negative x looks like this, negative x squared looks like this. So far, so good, right? And then we had plus 3x. It's nice because you don't have to put the multiplier in there. 3x is actually 3 times x, right? But it seems it's got it under control. Not like Maple, if you've used Maple before, in calculus maybe, then you have to put the multiplier in there and it's really annoying. 3x and then plus 4. So for every component that we add, it changes a little bit, right? And so if we just go through, so negative x squared plus 3, right, shifts it up 3, and then 3x, right, shifts it over, and then, and I guess changes it a little bit, plus 4. And then bump it back up, right? So it moves around. And here, it's even got, it's hard to see on here, but it's even got little points of interest, right? So little picture taking spots here. And so we've got the 2 places it crosses the x-axis. That could be fun to know. Where it crosses the y-axis, right? That might be good to know. And also, the vertex or the maximum, right? And so any extremas, right? So if you kind of click on one of those points, it'll tell you where it is. Hey, we knew that, we knew that. What would we have to solve for? We already did, right? We let t be 0, and we found that h of t is 4. And the only one we didn't solve for was this guy. We don't quite have the tools yet. Hopefully by the end of today we will, right? But the maximum is when x is 1.5 and y is 6.25. And so there's our maximum. And as far as these parabolas go, so this shape is a parabola, right? And so parabolas just keep going on and on and on forever. So in terms of our domain, right, in theory, if we keep going out long enough, it is expanding just slowly, right? So our domain is going to be negative infinity to positive infinity, okay? And the range, well, it'll never go past 6.25. So our range is everything less than or equal to 6.25, right? Because it's all the values of y. Okay, cool. Now let's see here. So the domain, we said, was from negative infinity to positive infinity. And we use round brackets, right? Because infinity is not a real place. The domain is from negative infinity to positive infinity. The range is going to be the set where x is less than or equal to 6.25. Sorry, f of x, h of t, sorry, just the range. I was dealing with a domain. Oopsies. H of t. Right. The output is going to be less than or equal to 6.25. Minimum, there is none, right? Because it keeps going and going and going. But there is a maximum. Maximum is at the point 1.56.25 from Desmos. Okay. Any questions about that? So play around with Desmos. It's kind of fun to have a look at what functions look like. And we'll use it again in a little bit here. But for now, we're finally moving into 1.2. And I really trimmed the fat on this sucker. So see how we fare. The problem with doing that is it makes your assignments harder, right? Because there's only so much that I can talk about, and then you're left to your own devices. But I guess that's growth, educational growth. So section 1.2 is on constant and linear functions. We've already seen linear functions, right, when we talked about stats where we fit the line of best fit, right? And so we have already seen linear functions. We'll say briefly, when we looked at lines of best fit. When we looked at lines of best fit. As a little refresher, right? A straight line has the form y equals mx plus b. So a straight line has the form y equals mx plus b. Where again, where m is the slope, and b is the y-intercept. For me, if I just say intercept, I mean the y-intercept. If I mean the x-intercept, I will specify. Okay? Because typically when we're talking about the intercept, we are talking about the y-intercept. This is where we have to keep track of, okay, a lowercase m, not the minimum, right? Because the context tells us so. Okay? So we're first going to consider a special case, right, where the slope is 0. Right? If we make the slope be 0, so m is 0, then we've just got y equals b. Right? So y is this constant value, and that's where we get our constant function from. Okay. So we will first consider the special case where m is 0, which gives y equals b, or if we're talking functions, f of x is b. But whenever you see f of x or h of t or whatever, I usually just read it as y, right? Because for me, in my mind, it's easier to think of that way, right? And so they're interchangeable. Which gives a constant function, or which will be a constant function. Okay, what does that mean? So when the slope is 0, right up here, well, the mx is gone, and so it doesn't matter what value of x you have, the output will always just be b, right? And so that's what makes it constant. So regardless of the input, I'll put in brackets x here, the output, which is f of x, will always be b. BB. So if we're thinking about something like this, right, we've got our x and our f of x, or y axes if you prefer. If we've got a line like this, zero, 3, for example, right? This is the line of f of x equals 3. And it keeps going and going and going. So whenever you have this completely straight horizontal line, you've got a constant function. Notice that the range of f, so if I asked you what's the range of f, the range, remember, is all possible outputs. There's only one possible output, and it's 3 in this case, right? But it'll just be b in general, right? And so it's the set of this one number, b. And so notice that the range of f of x equals b is the set of just b, right? Curly brackets around it. If we had to find a minimum or a maximum, that's kind of boring, right? But it's also a little bit strange because the minimum and the maximum are at every point across the domain. And the domain is from negative infinity to positive infinity, right? Because this line just keeps going and going and going and going. And so what happens is a constant function, it reaches its minimum and its maximum at the same time for every point of x on the set of real numbers, negative infinity to positive infinity. And so the value b is, in this case, both the minimum, lowercase m, and the maximum, capital M, of f attained at each value in its domain, which is from negative infinity to positive infinity. And when we write negative infinity to positive infinity, we have to use round brackets, right, for our set. So that's the special case of constant functions. So now we'll move into just linear functions, right? Straight lines. And so a linear function is a function of the form f of x is mx plus b, which we already said, but where m and b are real numbers, and to be a linear function, we cannot have the slope be 0 because then we have a constant function, right? And so we have to specify that with m not equal to 0. The domain, right? So what possible values of x can we have? Well, the domain of a linear function is from negative infinity to positive infinity again, right? We've just got a line on an angle somehow dictated by the slope, right? But it spans all values of x, right? Same thing for the range. It also spans from negative infinity to positive infinity. So the domain and range of a linear function is negative infinity to positive infinity. Yeah. If you try to find a minimum or a maximum, you're not going to find it because we range from negative infinity to positive infinity, right, on the y-axis. And so as soon as you find out the largest value, there's going to be a larger value, right, until you keep going to infinity. And so this means that there is no minimum or maximum. Therefore, a linear function has no minimum or maximum. This, I'll highlight this. That's a definition. So there's two ways that we can write a linear equation or a linear function. And so one is the point slope form and one is the slope intercept form. And so we've been looking at the slope intercept form, but if we want a more general case, then we can use the point slope form. I always get them mixed up. Point intercept or point slope. All right, so we can write a linear equation in two forms. The first one is in slope intercept form. Which is f of x is mx plus b. We've seen that one before, right? So if we say slope intercept form, that's the form that we mean. Our second option, kind of more versatile, is in point-slope form, which says that f of x is f of x not, it just means a subscript 0, right, or null if you want, but where I come from, we say x naught, h naught, that kind of thing. But it's possible that Allison and Frank might say h null or x null, but it's a 0. Plus m, which is the slope still, times x minus that x naught. Where the point x naught, f of x naught, is a point on the line. And then I'll put in brackets, m is the slope. But that's understood, yeah.
Is that sorry, in the brackets, x0,
Comma.
comma plus, or is that
Comma f of x. It's a sloppy f. Oh. How about that? So remember, these are ordered pairs, right? So we've got x naught and f of x naught. That's just one point on the graph. Okay. So I'll put a square around this because it's just highlighting two facts. If we're looking at the point slope form, oh yeah, yeah. Me neither.
are x0 and f of x0, they're going to be different.
That's right. So here, x0 is the input, right? And f of x0 is the output. We'll do an example. So try letting the point x naught, f of x naught, be 0b. The y-intercept, right? If I ask you to specify that, okay, well, x naught, f of x naught is going to be 0b, that's just specifying that, hey, the point that I'm looking at is the y-intercept, right? Forcing x to be 0, and then the output we know is going to be b. Right? So if we have the point slope form, f of x is f of x naught plus m times x minus x naught. F of x naught is b plus m times x minus x naught, which is 0. Which, if we swap the order, right, we end up at mx plus b. So f of x is mx plus b. And so we can go from this general form where it just says, hey, as long as you know one point on the line, I can give you the equation on this line, right? One point and the slope. Okay. Hence the term, this is the point slope, right?
Didn't you have a minus one?
Mm-hmm. Where?
Where the m next to the x minus 0, next to the second one.
This one? So I've got m times x minus 0, right? Because I'm forcing x not to be 0. But then x minus 0 is just x. Right? So they're equivalent, right? The first one that we're used to is just specifying, okay, I know the point that I know is the y-intercept, right? Or we can use this more general formula. If you just know a point on the line and the slope, then you can find the equation of the line. Okay. Just as a note, right, because it is going to be important, if we have a positive slope, right, we've got an increasing relationship. And so just recall that if we have something that looks like this, and m is greater than 0, our graph will look something like this. Right. It'll be increasing. Oops. We'll look at the other two instances. So if m is negative, then it's decreasing, making it look like that. Or if m is 0, then we've just got this vertical line, and then it's constant. It's sometimes the case that we've got a piecewise function, meaning, so we've got different behaviors at different points in the domain, right? And so we need to look at piecewise functions. And so it is sometimes the case that we need to represent function behavior by a piecewise function. So a piecewise function breaks up the domain and lists the well, the piecewise functions. I don't know how else to say it. And so a piecewise function breaks up the domain and lists the appropriate functions. And I'll say, and their respective domains. And their respective domains. So from this new set of examples, 1.2 and 1.3. So example 1 and 2 are from 1.2, and then example 3 is from 1.3. But because there's not that much, I just decided to put them on the same sheet. And so if we have a look at example 1, oh, I guess I need to grab it. Grab it, nab it. Authenticating error, whatever. I guess I'll try again. Oh yeah, is anyone else missing the examples? And I thought this one was pretty funny. Very clever, I'd say. They're very careful to not use brand names, of course. But so a popular phony smartphone carrier that is really funny and really clever offers the following smartphone data plan. And so we have this probably, right? And so you can use any amount of data up to and including 4 gigabytes, okay, for $60 per month. But then after that, there's an overage charge of $5 per gigabyte. Okay. So determine a formula that computes the cost in dollars as a function of using G gigabytes of data per month. And then we're gonna probably not sketch our answer. No thanks. Well, actually, I'll end up sketching it anyway, so I'll leave it in there. Okay. So I think if you had to kind of wrap your head around what this function looks like, right, you would likely, and this is why I guess I said I can't not sketch it, you would likely arrive at something like this, right? So for some amount of time, it's $60, regardless of how much data you use, right? So you've got this constant function. And then after 4 gigabytes, so all we know really is that here at 4, right, things kind of take off and I have to pay $5 per gigabyte. Right? So how do we make that into a function? Okay, so let's just talk it out, right? And so what we said here, that first section, was that from 0 to 4 gigabytes, we've got a constant function at $60, right? And so we know at this point we're at 60. Okay. And so from 0G to 4G, the charge is constant at $60. Okay. So far, so good. After 4 gigs, we need to add $5 for every 1 gig that we use. Okay, so let's write that out. So after 4 gigs, we need to add $5 for every 1 gig. I'll say gig. I don't know. Oh, my sneeze went away. We want to be careful though. We don't want to charge $5 for the 4 gigs that we get for $60, right? And so we want to adjust that so it's every gig on top of 4 gigs. Okay, and so so if G is greater than 4, we can find how many gigs we need to charge for, how many gigs we need, I guess, to pay for by G minus 4, right? Only because we don't want to pay for those free 4 gigs. Right. We don't want to pay extra for the first 4 gig. Yeah.
But if you use less than 4, you don't save money?
No, it's just a flat rate.
Well, yeah.
Yeah, in this case, yeah.
How do you define?
So we'll do it with a piecewise function. But for now, we're building up the hard part, right? That slope, the straight line. Okay. And so the g minus 4, that's what's being multiplied by 5, right, each month. And so g minus 4 is multiplied by 5. Each month. And added to the base price of $60. So we have something that looks like our initial $60 plus 5 times g minus 4. Right. This is only valid if the g is greater than 4. Right. So if g is greater than 4. Right. Anything before that was $60, yeah. Well, g minus 4 is multiplied by $5 each month. But we can actually ditch the each month. It doesn't add anything.
It would be g is greater than or equal to 4. If it was 4, if you use exactly 4 gigs, it would be
60. Yeah. Yeah, so it doesn't have the g greater than or equal to 4. It's just greater than 4 because even at 4, we're just charged 60.
Oh, okay.
Yeah.
So this is just absolute, like this. Sorry, this is just the amount. There's no consideration for time or values within time.
We're assuming that we're looking at per month,
yeah.
Right? So at the end of the month, you've got a bill, and that'll tell you how many gigs you have used. Yeah. Yeah.
So why wouldn't you just do something like say
Because assuming the x is representing the gigs, right, then you're paying 60 plus 5 for every gig, right, even the first 4.
Okay, I guess that makes what 60.
Yeah. Yeah.
Still have 0.
And so graphically, what you're talking about would look like this, right? Where you're just increasing by 5 each gig, right? Starting at 60. But we want to have this where we have 60, 60, 60, and then it takes off. Yeah. No. Okay.
Oh.
Yeah.
This is maybe getting a bit ahead, but like, are we gonna, is our formula gonna define like it goes in steps, like because it doesn't go in hard numbers. Like you don't pay like between 1 and 2 gigs, you don't pay like a fraction of 1.5 gigs.
No, so it goes. We're gonna skip that.
Okay.
Right. So as soon as you exceed an additional gig, right, you're charged that $5,
yeah.
Right, and then that $5, and so we're not going to reflect that.
Yeah.
But yeah, we're just assuming that they can charge constantly. All right, so g minus 4. That's the overage that we're charged for, is multiplied by 5 and then added to the initial 60 that we agreed to. Okay, and so let C of G be the cost function. So usually if we're talking about a cost, we use capital C as the name of our function, right? The cost function. then how we would write this is C of G is the piecewise function, and so we use a single curly bracket, and it just wraps around all our functions. I know I'm going to have two functions, right? I've got a constant function and then a linear function, and so I'll start with the first one, and so we know that G has to be greater than 0, right? 0 or anything positive, right? So between 0 and infinity, and so we know that there's a $60 charge if G is between 4 and 0, or 0 and 4. I guess I should have simplified this. The function for the additional charges, right? We can expand the 5 in, so we get 60 plus 5G minus 20 puts us at 40 plus 5G, which is 40 plus 5G. Just tack that in there, right? If we simplify, expand and simplify. And so I'll write that here, 40 plus 5G, if G is greater than 4. Right. Any G larger than 4 up to infinity, we use that function.
Why is it 40 and not 20?
Because I pulled a fast one here, and I said, okay, well, 60 plus 5 times G minus 4 is 5 times G plus 5 times negative 4.
Oh.
And so I've got 60, and then plus 5G minus 20, 60 minus 20.
Oh,
that's
okay.
how I got the 40.
Yeah.
But I forgot to expand it up there, so I just snuck it in. Okay, so, right, if we had to sketch this, right, our constant function, so we already did, but let's do a proper one. So I know I have G up on the x-axis and C of G on the y-axis, picking a point, kind of an arbitrary point. Let this be 60. Then this point is at 4, right? So we've got 1, 2, 3, 4. Here, this was up to and including G equals 4, right? And so what we do is we do a full circle, and then what we want to make sure is, and it will, but what we want to make sure is that when G equals 4, even though it's not supposed to here, right? When G is 4 in this equation, we just want to make sure that we're actually going to start where we think we're going to, right? Because it's possible that we'll have a little jump here, right? Maybe there's a penalty, right? So a $20 penalty, for example, then, and then that's where it starts, right? So that's possible. And then we would just draw it with a round circle, but just to check. Okay. So check 40 plus 5 times 4 is 60. Right. So we start at 460, which is what we thought it was going to do, but we just want to double check. And then to draw any straight line, what we need is 2 points on that line, right? And so we already checked, right, that 460s on the line, right? And so here's one point. And so in order to draw this linear equation, right, properly, we need to find another point on the line. But we can do the same thing where we just say, oh, what if I force G to be 6, for example? And then I'll know at 6, it'll be some value that I can plot. And as soon as I have 2 points, I can connect those and extend the line, and then we're done. So to draw 40 plus 5G, we need 2 points on the line. We already found 460. Let G be 6. You can pick any value, right? But just let G be 6. Then we find that 40 plus 5 times 6 is 70. How about, to make this nice, right? What I'm struggling with here is that I made this be equal to 60, and then to make 70, that would be like here. It's not very good, right? And so what I'll do is I'll just indicate that there's a break here, like this. And then I'll just say that up here is 70. Make it loftier, right? I can do that. And because I'm just sketching this anyways, at 670 is my second point. And here's 460. Now that I have these points, you take any straight edge. I just take some paper, connect these two, and extend the line. Ta-da. Drawn a straight line. Okay. So to draw a straight line, all you need is 2 points on the graph. Okay. Any questions about that one? So that's a piecewise function, right? Yeah.
Piecewise functions just have like an unlimited amount of instructions. Like you can just keep writing more conditions and plot whatever you wanted to.
Yeah. So there's something called the floor function, where it takes a number and it just drops you down to the lowest whole number, right, or the nearest whole number, and so and always drops down. And so that drawn out is just a bunch of steps, but it keeps going to infinity and infinity.
It's useful for this one to make like the it only click over when it's, or you could you make like your inputs only whole numbers or something to define it? Like
yeah, you could. Yeah, but for us, we're dealing with a continuous function, so we're gonna pretend it's continuous, but. Cool. Let's have a look at example 2. Okay. So it's the same Skippy's data. Okay. So when we have ordered pairs like this, 0 and 64, 2 and 67, we can use Desmos. And I'll just ditch this line here. And if you go up to the menu, I guess, up here, it gives you a bunch of kind of prefab options. And so one of those is the the statistics linear regression, which you did on assignment 2, but now I'm going to show you kind of a cooler version. Okay. And so what it does is it gives you some default values. So we're going to replace these x's and these y's with our values, and it'll just update it. And what's going to happen down here is it gives us the r squared, right? The r squared, remember, tells us how good good of a job the line will do at predicting new values, right? And then it gives you the slope and it gives you the intercept of the straight line, right? The line of best fit. And so let's see here. So if we go through and we have 0, 2 is 2, 3, I'm going to change to 4. Come on. Oops, not 5, 6. So finicky. 6, 8. Come on. 10 and 12. $64 for the y, right? And as I'm changing, it just goes through and it changes with whatever I do. 75, 80. Now it's behaving. 83. Oh, as I said that, I gave it praise. Can't give technology praise. 83, 83, and 82. Come on. Phew. Okay. Here, we have to zoom out, right? Because if we're looking at our y values, right, they're up here in the 70s, 80s. Right? And so here, right, we've got our line of best fit. The slope is 1.67857 and the intercept is 66.2143, which, I mean, if we're looking at this line, right, the line of best fit, 66.2143 looks reasonable, right? And so it just gives us that information. And so if we part A, using Desmos, we find that f of x, could do f of t or t of t, lowercase t of capital T or something, because it's time and temperature, but f of x is mx plus b, which in our case, we had a slope of, does anyone have it?
1.67857.
1.67857 x plus the intercept was 66.2143. Awesome. Right, and so this is our line of best fit. And it also gives you the r squared, but. So for part B, use the model. So this is the model of this relationship. And so this is what we're kind of more familiar with, right? To predict the temperature at 7 a.m. So in terms of our x's, right, or our inputs, 7 a.m. is 1 hour after 6 a.m. Right? And so really what we want is f of 1, which is 1.67857 times 1 plus 66.2143. So 1.67857 plus 66.2143 I get 67.89287 degrees Fahrenheit. Right, so at 7 a.m. we predict the temperature to be 67.9 degrees Fahrenheit. So the way this is structured, right, the input is taking the hours after 6 a.m. And so 6 a.m. is denoted by a 0. And so we have to keep track of how these inputs are being done. All right, so I'm plumb out of time. And we didn't get to 1.3. And so I guess the assignment is due on Thursday, not Tuesday. So make sure you change that. Yeah. Because you won't be able to do that last question anyways. Yeah. So until Tuesday, so make sure you change that due date to Thursday. Sorry, guys. That is so nice.
All right, so